Okay, so let's say we have this level curve where on the left side we have a function of x and y, and on the right side we just have a constant. And let's just say we're trying to look for the slope of this. So we're trying to look for dy dx, pretty much. And the way we're going to do that right away is we're going to take the derivative d dx on both sides of the equation, not the partial derivative, but like the full-on derivative. So d dx of f x y, then likewise for the constant, d dx of the constant. On the right side, it's kind of clear the derivative of a constant is just going to be 0. So we have our 0 here. And on this left side, we're taking the derivative of a multivariable function. This is like a Calc 3 topic. So when we differentiate this function, I should also note that y is a function of x as well. So y is a function of x. So when we differentiate this, we're going to get the partial of f with respect to x times dx over d of x plus the partial of f with respect to y times dy d of x. Now that we're here, we notice that this d of x over d of x, that's just going to be 1. So we can go ahead and get rid of that. So we have, right here, we just have the partial of f over the partial of x. And now we could just solve for dy dx from here on out. So when we solve for dy dx, we get negative, because when we take this to the left side or to the right side, it's going to turn negative. Then we're dividing by this term. So we're going to get negative the partial of f with respect to x over the partial of f with respect to y. So here is where we have this equation now. We're going to do a little tampering with this. So for this top function, this partial of f with respect to x, we're going to let this equal to m of x. So because f is a function of x and y, the partial of f with respect to x could also be a function of x and y. So we're leaving it like that. Likewise for the bottom. So we're going to call this one n of x and y. And at this point, what we could do is do the butterfly method. So when we do that, we get n of xy dy is equal to m of xy d of x. And also don't forget the negative right here. So now we could just get everything on one side, and that's where we're left with this equation, which you're probably familiar with. We get n of xy dy plus m of xy dx is equal to 0. And here, there's the condition that we want to follow, that if this differential equation has an exact solution, then the partial of m with respect to y has to be equal to the partial of n with respect to x. Because I don't know what rule it is by derivatives, but when you take the derivative of f with respect to x first, then y, that has to be the same to taking the derivative of respect to y first, then respect to x, then we get x and y. So these two are pretty much the same thing. But yeah, as for the proof, this is what we have, where our n of x, we have this. This is just equal to the partial of f over the partial of y. Then as for m, we have m of xy is equal to the partial of x with respect to x. So this is pretty much everything that we're going to be using for this video. And yeah, on to some problems. Okay, so here we have a differential equation, 2x plus y dx plus x minus 2y dy is equal to 0. So from before, we know that this part right here, this is just going to be m of x, y. And this part right here is going to be n of x, y. And by definition, those are going to be the partial of f over the partial of x. And same thing with this one. This one by definition is going to be the partial of f over the partial of y. And with this, we're able to solve for our function. Yeah, we're able to solve for our function, which then we could pretty much just plug in to our first equation from the very start. F of x, y is equal to c. So once we're able to solve for our function, we could just plug it in here and pretty much get our answer for this differential equation. One thing to note, the reason why we might want to solve for a differential equation this way is because sometimes we're not able to separate the variables together. So say something like dy dx is equal to a function of g times a function of y. Like in some cases, sorry. Okay. So in some cases, we're not going to be able to get it in this form. And same thing with putting it in a linear form. So something like dy dx plus a function of x times y is equal to a function, another function of x, g. Which is why sometimes we got to go with this method. So besides that, this is how we go about solving a differential equation when we can't use those other two methods. However, most of the time, because of this, it's going to be an implicit solution. We're not going to be able to solve for our function explicitly. However, nonetheless, it is a solution. Okay, so with this, we know that 2x plus y is equal to the partial of f with respect to x. So we could just do this, the partial of f. And this is going to be equal to 2x plus y. And as you may have guessed, we're going to integrate both sides with respect to x. So we're going to, I just erase so that way I could have a bit more room. But we have that is equal to the integral of 2x plus y d of x. Okay, so at this point, y we can treat as a constant. So our function f of xy is going to be equal to x squared plus y of x. And we do have to add a constant. However, our constant is going to be, sorry about that. Our constant is going to be in terms of y. Because if we took the derivative of this with respect to x, this should also go away even if it's a function of y. So this could be a constant, like just a number like 2, 3, 4, or this could be anything, a function of y in a sense. This cannot have any x terms in it. Okay, so at this point, we're just gonna have to solve for this to get our actual function. Then we could just plug back in here. So in order to do that, we're gonna take the partial of y. The reason why we're taking the partial of y is because we already know by n, this is a partial of f, the partial of f with respect to y. So on the right side, we're also doing the same thing. I'm just not gonna write it. So we have the partial of f over the partial of y. When we take the derivative with respect to y on this part, this goes away, and this is just gonna be left as x. Yeah, x, and then as for this, we're gonna leave it as f prime of y. And right here we have our partial of f of y. This is going to be equal to x minus 2y. So I'm going to replace this term right here, x minus 2y. And we're just solving for this partial of f. So these x's go away, and we get negative 2y is equal to f prime of y. And at this point, what we could do is just integrate. Then we're able to solve for f of y. So we're gonna erase that. We're gonna integrate negative 2y dy is equal to the integral of f prime of y dy. And when we do that, we get negative y squared is equal to f of y. So now that we have that, we can just plug it into our formula. So our solution, or not our solution to this, but our function that we're dealing with is going to be f of x, y, is equal to, not 2x. This is going to be equal to x squared plus y of x. Then our f of y is just negative y squared. So right here is our f of x, y. And this is where we just plug it into here. So the solution for this differential equation is going to be x squared plus yx minus y squared is equal to some constant. So this is our solution for this differential equation, which was this one. Okay, that's one problem. Let's go on to another one. Okay, so here we have another differential equation. It's a bit more complicated, but now we have this initial value problem. So that way, at the end, we're gonna have to plug in these values and actually get a get an equation really that crosses through this point. Okay, we could go about the same approach as we did with the other problems. So this part right here is gonna be m of x, y. So we're just gonna set this equal to the partial of f with respect to x. So here we have partial of f with respect to x is equal to y e to the xy minus 1 over y. We can do the same thing and integrate both sides with respect to x. So that will give us the function of x and y. When we integrate this, we're going to be left with e to the xy. And this 1 over y is just treated as a constant. So we have minus 1 over y of x. Yes. And don't forget about our constant, which our constant is going to be in terms of y. And we're pretty much doing the same thing. We're going to find what this constant is. And once we find that, we can let it equal our f of x, y is equal to c, and just solve for that. Plug in the initial value problems. Okay. So from this point, we're just going to take the partial of y on both sides. And I don't have room here, but I'm taking the partial of y on both sides. So we get the partial of f over the partial of y. When we take the derivative of y on this side, we're gonna get this e to the xy. We're gonna get, we're gonna get x e to the xy, okay? And when we take the derivative on this part, we're going to get plus 1 over y squared of x. Again, x's here are being treated as a constant. And this right is just going to be f prime of y. We know what our df dy is from this part. So right here, n of xy, which is equal to the partial of f over the partial y. So we're just going to plug that in. When we do that, we're going to get x e to the xy plus 1 over y squared of x. And this is just going to be equal to that. And this is really convenient because this term cancels out, this cancels out, that goes away, and that goes away. And we also have our f prime of y. So our f prime of y is going to be equal to 0. And we're just going to integrate both sides. But as you can see from at this point, 0 is going to be equal to f of y. And because y is a function of x, we don't have to worry about a constant on the left side. So it's just going to be 0. So now that we know what f of y is, our function, so f of xy is going to be equal to e to the xy minus 1 over y to the x, and our f of y is just 0. Okay. So now we just have that. So now that we have that, we already know that f of xy is equal to c. This is our level curve, and we just plug it in. So we get e to the xy minus 1 over yx is equal to c. Now this is the general solution for this differential equation, but because we have an initial value here, we're just going to plug in x is equal to 1 and y is equal to 1. So when we do that, we get e minus 1 is equal to c. So now the solution for this initial value problem is going to be e to the xy minus 1 over yx, and this is equal to e minus 1. And that is going to be our solution for this initial value problem. And yeah, one more example. Okay, so now we have this differential equation. However, here we have n of xy, and pretty much what we're gonna do is solve for n of xy that will make this differential equation exact and have a solution and pretty much be able for us to obtain a solution using the methods that we've already used. So yeah, let's just get right into it. So for this one, if we're looking for exactness, pretty much, we know that from the beginning, the partial of m with respect to y has to be equal to the partial of n with respect to x. So this signifies exactness. And what we know is that here, this part, this is m of x, y. So we could just make a quick plug-in right here. So we have the partial of y, then we have our function. So we have this xy plus e to the x, and we just have our partial of n with respect to x. So on the left side, we're just going to differentiate with respect to y. When we do that, this first part, we're going to have to perform a product rule. So we're going to take the derivative of y, which is just 1, and leave the second part alone. So we have cosine of xy. Then we're going to leave the first part alone, so plus y, and take the derivative of this second part, cosine of xy. Which, if we take the derivative with respect to y, that's going to be x. It's going to be negative sine of xy. Okay. And as for this e to the x, that's just a constant in the y world. So this just turns it to 0. So this is going to be equal to the partial of n, the partial of x. Okay. And at this point, if we're solving for n, we're going to integrate both sides with respect to d of x. And then that will give us our n. That will pretty much solve for n in this case. So when we're integrating this side with respect to x, y is treated as a constant now. So pretty much what we did, first, we just took the derivative of y first, and now we're gonna integrate with respect to x, pretty much. Okay, so for this part, we're treating y as a constant. So the integral of cosine of xy is gonna be 1 over y sine of xy. And then for this next part over here, we're gonna have to do a tabulars method or integration by parts. So I'm gonna do the tabulars method. So di plus minus plus. I'm going to take the derivative of the product of y and x. So y and x. And I'm gonna be integrating this part, sine of xy. And as I go down the row, taking the derivative with respect to x, it's going to be y of x, then y, then 0. Same thing with this part. I'm going to integrate down the row with respect to x. So we're going to be left with 1 over y, negative 1 over y, cosine of xy. Yeah, okay. And when we integrate again, we're going to get negative 1 over y squared, and this would be sine of xy. So our solution for this integral is going to be here in the diagonals. We're just going to multiply these two together plus the product of these two. So pretty much this product plus this product. So we're going to get, also just because there's a negative sign here, we're gonna have to worry about a bunch of negatives. So we have a negative here and a negative here. So this first part is gonna be positive. The product of these two are gonna be x cosine of x and y. And we have a negative here, negative here, negative here. So we're gonna still be left with a negative there. And the product of these two is just going to be 1 over y sine of x, y. And this is going to be equal to our n of x. Or our n of xy, really. And this term cancels out. Actually, I forgot to bring up one part. Because when we integrate this with respect to x, we're also going to be left with a constant f of y. So that's going to be our n of xy. And again, this term cancels out and this term cancels out. So the equation to make this differential equation exact is going to be x cosine of xy plus f of y. So now here we have our solution, or really this could be many solutions to this differential equation as long as this stays in terms of y. And yeah, hopefully this video helped you out. And yeah, see you guys.